Regarding the notions of Riemann-Roch codes in terms of algebraic function fields, now we define Goppa's algebraic code construction from algebraic curves. For this purpose, let me first fix a function field f over a constant field, finite field fq of genus G. And like in the Riemann-Roch case, let me fix n pairwise distinct rational places. Pairwise distinct places in given function field f. So that means their residue class field is isomorphic to constant field fq. And to represent these distinct places, let me set a divisor as a sum of these rational places. And separately, we consider a divisor G whose support does not contain any given distinct places Pi. So it has different support from the support of D. And indeed, this condition is necessary because when we define the evaluations of the functions from the Riemann-Roch space of G, given at n distinct places Pi's, this definition should be meaningful. So that means when we consider a function and when we evaluate these given distinct places, so that means it has no poles at these Pi's. So that means the images cannot be infinity. So that means there's no like a inflection at any coordinates. So that means these evaluations are not infinity. So this definition makes sense. And as you may guess, the image of this evaluation map will be defined as an algebraic geometric code. And we will use the notation CL or CL of D and G to represent the given places and the given divisor. So indeed, this set is called, let me also use this as the image of evaluation D. And this set is called algebraic geometry or geometric codes. And we will often use AG code, we will say often AG codes in short. And obviously this, I mean, this evaluation again, FQ linear map, we can easily see that. This is FQ linear map. Let's check. So that means images also is FQ space in FQ to the n. So that means they are obviously linear codes. And evaluation map is surjective onto this code, linear code C, obviously by definition. And in Riemann-Roch codes, we have observed that indeed the kernel of such evaluation, when we consider the rational function fields and particularly the places of the rational place P infinity of degree K minus 1, when particularly this divisor, indeed we have observed that this evaluation map is injective, but this is not always the case. And in the next theorem, more explicitly, we can estimate the parameters, the dimension and the particular minimum distance in terms of the dimension of the and the degree of this given divisors. More explicitly, we will see that in this case, these evaluation map are not supposed to be injective always. So its dimension can be less than the dimension of our image, our pre-image space. And the minimum distance is bounded below n minus the degree of given divisor G. And so first, let me show that. So to see that its dimension is the difference between the dimension of G and G minus D, it's enough to observe that the kernel of this evaluation map is isomorphic to the Riemann-Roch space of n minus D. And then by using first isomorphism theorem, we can conclude that it has dimension K. So if you want to see how the kernel looks like, so that means we have functions, they have zeros at given each FQ, so that means given each residue class fields. So if the evaluation belongs to, for instance, if f of x p1 is equal to p1, means that by the definition of the evaluation, if we have zero coordinates, so that means the function is supposed to have zero at given places p1. More explicitly, if we use the discrete valuation maps, being in the kernel means that valuation of x at pi is strictly positive. And if we write this divisor G more explicitly in terms of the places, if we denote them like this, which has different disjoint supports from D, by the definition of the Riemann-Roch theorem, we know that the principal divisor of x is bigger than or equal to minus G, and because they're also in the kernel, so that means for each pi, this is also bigger than or equal to this quantity, strictly bigger than this quantity. And indeed, this shows up that this functions has also zeros, this given pi, and indeed this shows that this functions also lies in the Riemann-Roch space of G minus D. And by the first isomorphism theorem, indeed we can see that the image of the evaluation map is isomorphic to quotient space of L of G over L of G minus D, and this shows the dimension is the difference of the dimensions of two divisors G and G minus D. And for the minimum distance, let me consider non-zero code word from C. So that means, indeed, by the definition, it is going to be evaluation of a function or the image of a function under the evaluation map. And since it's a non-zero code word, it's going to have non-zero weight. So if it has weight d, so that means there are n minus d coordinates which has this function, this code word has zeros, because weight constant the non-zero positions of the code word. Let me denote the coordinates which contains 0 from I1 to in minus d. And like in the previous case, if it has 0, if this function has 0 at the given this bis, that means its valuation at this place is strictly positive. Then so for x in L of g, we get, if we apply the definition of the Riemann-Roch space, together with this definition and this assumption, we will see that the principal divisor of x indeed can be written as g minus pi1 up to pi n minus d. Then indeed we can say that this non-zero function x is non-zero because we suppose that C is a non-zero code word. Lies in the Riemann-Roch space of the differences of G and the summation of the zero positions. So, so if it contains a non-zero code word, so I mean, maybe it's better to write it. So we, from corollary 1.4.12, we know that when the degree is negative, the Riemann-Roch space is going to be trivial space. The dimension is going to be 0. But if the dimension is not 0, so that means if our Riemann-Roch space is not trivial space, by the contraposition, we can argue that the degree is supposed to be, degree A is supposed to be bigger than 0. So in this case, this Riemann-Roch space is not trivial because it contains non-zero function x. So that means its degree should be bigger than or equal to 0. And the degree of this difference of these two divisors is the degree of G and the degree of the sum of these rational places. So we have all of them rational, and total we have n minus d distinct places. And indeed, this inequality shows us that the distance of, weight of any code word is bounded below n minus degree of g. I think I made a mistake. Couldn't be sure where. So 0, our claim is to show that degree is bigger than or equal to 0, n minus degree d. Yes, okay. So this is, so if it is holds the, for weight of any code word, so the minimum distance of our algebraic geometric code is bounded below n minus degree of g.